Welcome back. So let's think about the Bohr hydrogen atom and think about the forces that might be exerted on an electron that's orbiting a proton in a circular orbit of radius, let's call this r, and moving at velocity v. So let's think about what forces might be going on here. And probably you realize that the most important force that matters is the electric force, right? So things like gravity, the gravitational attraction between a proton and electron is negligibly small compared to the electric force exerted by my proton. So I'll just, on my electron, I'll label that as F sub E. Right? And this is a good thing, right? Because you know that there needs to be, right, that if you have something that's going in a circle, there is a radially inward acceleration, which means that you need to have a radially inward net force. That's exactly what this electric force is. And notice that the force is attractive because we have two opposite charges here. So applying Newton's second law, right? So let's first remind ourselves what this force is. So according to Coulomb, right? I'll just work with the magnitude of the electric force rather than sort of define like an r hat vector. But you know that the magnitude of this electric force goes like the Coulomb's law constant, right? So and that's 1 over. So I don't know if you wrote k or what in 118, but we'll use 1 over 4 pi epsilon naught times our charges, right? And so or the magnitude of our charges. So a proton has charge E, as does an electron. So this will go like E squared. And then you know as well that Coulomb's law, electric forces are inverse square forces. So this goes like 1 over r squared. So now, right, we need to think about applying Newton's second law, right? So and that tells us that mass times acceleration equals F net. But the net force, the only relevant force here is this electric force. So let me just write F net equals F E. We can get away with working with magnitudes here, so I'm just going to do that. So if I take the magnitude of this, of both sides, I have the mass of my electron, right? That's a particle we're considering the forces on, equals the magnitude of my electric force. Now, if you think back to 117, right, we talked about what the magnitude of the acceleration for an object undergoing uniform circular motion is. And we learned that the acceleration has a magnitude v squared over r. So we have our acceleration, and we already found, right, what the magnitude of the electric force is. So if I plug that in over here, right, we now have a relationship, right, between the velocity of our electron and the radius of the orbit. Then we can go on and simplify this further if we wanted to, but I'll just leave it in this form for now. Okay. So that's the first ingredient that goes into Bohr's model of the hydrogen atom. The second ingredient is some early quantum ideas, namely the idea of the de Broglie wavelength. Right? So let's call that A. Right? So de Broglie, right, says that the electron has a wavelength lambda equals h over p, or h over m v, right? So the goal, right, is to is what we'll do is we'll try to rewrite this in terms of the electron wavelength, the N2L equation. So I'll erase the board and then we'll roll back over and continue. Okay, so here again is what Newton's second law tells us, and here's what de Broglie tells us. And the goal is to use this to eliminate V. And we can do that in the following way. So since we have a nice expression for the momentum m, the magnitude of momentum mv from de Broglie, I'm going to actually start by trying to rewrite this in terms of the momentum. So from here, right, we have, right, m magnitude of v, the quantity squared divided by m over r. Take a second and look at this and convince yourself that that is in fact the same as here. I've just sort of multiplied by m over m. So I have that here, and that equals my right hand side. And now I can plug in de Broglie, and so I get h, so if I have h bar over lambda squared here, so I have h squared over lambda squared m r equals 1 over 4 pi epsilon naught e squared over r squared. So the next step is that Bohr had to take was to apply a quantization condition. So this is sort of something that might be plausible in analogy to what we did for the infinite square well. Let me just state it, and then I'll actually have to go to my computer because I cannot draw this, and then we'll come back. So, so step C, or ingredient C, is our quantization condition. And the Bohr quantization condition here is that an integer number of wavelengths has got to fit around an orbit. Fits. Right. Therefore, right, so you can have, right, one wavelength equaling so an orbit, so namely n lambda equals 2 pi times the rate r, right? So 2 pi r, right? This is the circumference of my orbit. Orbit circumference, right? So I can have like one wavelength equal to my circumference. I could have two wavelengths equal to my circumference, etc. So here, this is an integer. Let me now cut to my computer so I can show you a picture of what this looks like. As I mentioned, this quantization condition is hopefully reminiscent of the infinite square well, right? Where you could only have, and you have integer multiples of half a wavelength fitting within the well because the wave function had to vanish at the edges. So this is sort of similar in spirit to that. So to derive the allowed orbits, the allowed orbit radii, which is namely the r's here, right? We're gonna need to do, what we'll do is we'll plug in this quantization condition here where there's a lambda, and that will eliminate the lambdas and will allow us to solve for the allowed radii r. Let me erase the board and then we'll do that. So as I said, what we'll need to do is to plug this quantization condition in over here for lambda. So let's do that. So I'm going to have to divide by, I'm going to have lambda squared downstairs. So so this gives me, right, lambda over 2 pi equals 2 pi r over n. So when I have 1 over lambda squared, I'll get an n upstairs, n squared upstairs. So I have n squared h squared. Okay. Now the rest of my lambda, I have 2 pi times r, the quantity squared. Now because there's an n dependence on this, right, there are different allowed wavelengths for each value of n. I'm now going to switch to labeling my r with r sub n to denote the radius associated with a particular value of n. So doing that, right, we have now an m here and an r sub n there. And then on the right, we haven't done anything yet, so we still have Coulomb's law. Only this time, right, I'm gonna change that to an r sub n, so let's just I'll label this as radius and orbit. Right. Okay. At this point, right, we have stuff that depends on r and constants. So it's going to be algebra to solve for r sub n. So solve for r sub n. So let's be strategic about this, right? So notice, right? So a few things. Let's see. So notice that we have an r sub n squared here and an r sub n squared there. So I can actually cancel that. I'll cancel this, which leaves me with 1 r sub n here. I basically need to shove this over to the other side and shove everything else over. So if I do that, so I'm going to sort of flip the equation around. Let me multiply both sides by, so I'm going to r sub n, right? So I get r sub n, and then over here, and then I'll just divide the old left-hand side by all of this. So let's just get the whole left-hand side first. So we have an n squared h squared, 2 pi quantity squared, so that's a 4 pi squared times an m. We already took care of the r sub n. And then now I need to invert this, so I've got a 4 pi epsilon naught upstairs and an e squared downstairs. Take a look at that for a second, convince yourself that this is all legal. And then, right, if I simplify this, right, we get, right, so I have an n squared and an h squared. So the 4's cancel here. Right. By pi, I'll get a 1 power of pi downstairs. So I have a pi, so I have an m e squared, but let's not forget our epsilon naught. Right. So that's r sub n. It turns out to be a little bit more traditional to write this in terms of h bar. So I'll do that, and h bar, right, you know, is just h over 2 pi. So right, let's width. So if I do that, what we have is then n squared. H squared is going to be h bar times 2 pi. Quantity squared over times epsilon naught. And then we have a pi m e squared. So when the dust settles, making sure I have all my factors of pi, we get for the allowed radii n squared h bar squared times 4 pi epsilon naught over me squared. So I've restated our result for the allowed radii here. So notice that as n increases, right, the higher n orbits are further out, as we might sort of intuitively expect. There's one sort of piece of terminology that I want to define, because it's something you'll see in like atomic physics. And that's namely the Bohr radius. We'll use A sub b for Bohr radius. And why the Bohr radius is relevant is that it sort of roughly sets the length scale for the size of an atom. And the Bohr radius is just these fundamental constants, this group of constants when n equals 1. So this is r sub 1. So the Bohr radius ends up being h bar squared times 4 pi epsilon naught electron mass divided by and fundamental charge squared in the denominator. You can go and convince yourself that this really does have units of length. It has a numerical value of about 5.29 times 10 to the minus 11 meters. So if you want to think about like the size of an atom as like roughly double the radius, so this is, so 5 times 10 to the minus 11 times 2 is about 10 to the minus 10. So that's why, like, as a rule of thumb, you can say like the size of a hydrogen atom, order of magnitude is about 10 to the minus 10 meters, or you might have seen the unit before, 1 angstrom. We'll say more about that next time. I want us to close with a clicker question, thinking about how this approach could be applied to a hydrogenic ion, so something that still only has 1 electron orbiting a nucleus, but this time it's going to be a helium nucleus. So for our helium plus ion, right, we have, right, the nucleus has a charge (2e). So remember where the charges appear in our expression for the allowed orbit radii. Both of the e's here in the denominator, right, they're in the denominator. One came from the proton in hydrogen, the other from the electron. Right, if we were to replace one of these e's with 2e, right, I think you can see that the radius of the n equals 1 orbit would go down. And 1 orbit smaller. And you can sort of qualitatively think about this, right? As if I double the charge of the nucleus, I now have a stronger force that's pulling me toward me, the electron, towards the nucleus. So maybe it's not too surprising that the allowed n=1 orbit is indeed smaller. So when we come back in the next class, what we'll do is we will wrap up the discussion of the Bohr atom. We'll look at the energies, which will let us predict the spectrum of hydrogen. And then we'll take a short look at how quantum mechanics works in 3D, so that we can take a peek at the Schrödinger hydrogen atom on Monday. See you then.